Washington, D.C., January 10, 1941. A stack of memoranda sat on Admiral Emery Esland's desk, each page dense with columns of losses and projections. The numbers told a story the public did not yet know. British merchant ships were vanishing beneath the Atlantic at a rate of 7 million tons per year. Traditional American shipyards, using riveted construction, required 230 days to complete a single cargo hull. The mathematics were simple and brutal. Replacement could not match destruction. Admiral Land studied a photograph clipped to the top file, a Liberty ship blueprint, still theoretical, still unproven. The proposal promised welded hulls in a fraction of the time. It seemed impossible. But across the hall, Maritime Commission planners were already calculating what would happen if it worked. They did not yet know that within 4 years, a ship would be built in 4 days, or that this single breakthrough would decide who controlled the seas. In the first weeks of 1941, the crisis facing the United States Maritime Commission could be reduced to a single, unforgiving equation. Britain was losing cargo tonnage faster than the Allied nations could replace it. Every month, German U-boats sent thousands of tons of merchant shipping to the ocean floor. Every month, American and British shipyards struggled to deliver new hulls using construction methods that had changed little since the previous century. Admiral Emery Esland, chairman of the Maritime Commission, understood the arithmetic of attrition. His desk held summaries from the British Ministry of War Transport documenting losses that exceeded 1 million tons in some quarters. Against this, United States yards were completing cargo ships at an average rate of 1 hull every 230 days. The bottleneck was structural. Riveted construction required sequential work. Hull plates could not be installed until frames were in place. Compartments could not be sealed until hull work was complete. Each ship needed 10 to 12 million rivets, each rivet requiring skilled labor and time. The berths themselves became the constraint. A shipyard could only build as many ships as it had berths, and each berth remained occupied for 7 to 8 months per vessel. Maritime Commission planning tables, stamped January 1941, showed throughput curves that could not bend upward without a fundamental change in method. Man-hours per hull hovered near 1.2 million. Material waste ran high. Training bottlenecks limited expansion. And every week, the convoy reports from the Atlantic grew darker. In the first quarter of 1941 alone, British imports fell by nearly 1/5. Food stocks tightened. Munitions deliveries slowed. The Prime Minister's cables to Washington carried an increasingly urgent tone. Britain needed ships, and it needed them faster than any peacetime shipyard had ever delivered. Admiral Land knew the numbers by heart. He also knew that somewhere in the stack of proposals on his desk was a plan that might break the equation. If it could be proven, if the risks could be managed, if American industry could be persuaded to abandon a century of orthodoxy. By March, he would face a contractor who had never built a ship, proposing a method that traditional shipwrights considered dangerous. The stakes could not be higher. Without more hulls, Britain's import program would collapse. Without Britain, the war in Europe would be lost. The Commission's internal memos from early 1941 reveal the scale of the challenge. One planning document estimated that sustaining Britain's minimum import requirements would demand an additional 400 cargo ships within 2 years, an output that would require doubling or tripling current production rates. Using conventional methods, such expansion was impossible. The skilled labor simply did not exist. The berth capacity could not be built fast enough. Even if every existing yard worked at maximum capacity, replacement would lag behind destruction. The solution, if one existed, would have to come from outside the shipbuilding industry itself. It would have to come from someone who saw ships not as craft but as products, someone who understood mass production, standardization, and the brutal efficiency of the assembly line. That someone was already preparing his proposal. Washington, D.C., March 6, 1941. The briefing room at the Maritime Commission was not accustomed to presentations from contractors with no shipbuilding experience. But Henry J. Kaiser was not a typical contractor. He had built dams, highways, and pipelines. He had mobilized tens of thousands of workers on projects that required moving mountains of earth and concrete on schedules that traditional engineers said were impossible. Now he was proposing to do the same with ships. Kaiser's presentation was blunt. The problem, he argued, was not ship design, it was ship construction. Riveted hulls required sequential assembly, which meant idle workers and idle equipment. Welded hulls, fabricated in modules at off-site locations, could be assembled in parallel. Instead of waiting for the hull to be built before installing machinery beds could be welded into prefabricated sections and lifted into place by crane. Instead of riveting plates one at a time, entire bulkheads could arrive complete and ready for installation. The numbers Kaiser presented were startling. He claimed that modular, welded construction could reduce build time by 30 to 40%. Weight savings of approximately 60 tons per hull would reduce steel consumption. Labor hours per ship could drop below 600,000. And most importantly, the bottleneck would shift from berth time to module production, a constraint that could be solved by building more fabrication shops, not more shipyards. Admiral Land listened carefully. The Maritime Commission's own engineers had studied welding, but they remained cautious. The industry's conventional wisdom held that welded seams were brittle and prone to cracking, especially in cold North Atlantic waters. Master welders were scarce, and the technique required precision that yard foremen doubted could be achieved at scale. But Kaiser was proposing something more radical, training welders in weeks, not years, using standardized jigs and fixtures that would control quality through process, not through individual skill. The proposal was backed by preliminary engineering studies. Electric arc welding technology had advanced significantly in the previous decade. Fixture jigs could hold sections in precise alignment, allowing even novice welders to produce acceptable seams. Centralized quality assurance using X-ray inspection and destructive testing of sample coupons could catch defects before they reached the hull. And 24-hour shifts, running continuously, could maximize equipment utilization in ways that traditional daylight-focused yards never achieved. The Commission faced a decision. Approving Kaiser's plan meant committing hundreds of millions of dollars to an unproven method. It meant overriding the objections of experienced shipbuilders who warned of structural failures and cost overruns. It meant betting the Atlantic supply line on the word of a dam builder. But the alternative was to continue losing the tonnage war at current rates, a course that led, with mathematical certainty, to defeat. On March 27, 1941, the Emergency Shipbuilding Program authorized the construction of Kaiser's first emergency shipyard at Richmond, California. The plan called for building 200 Liberty-class cargo ships using welded, modular construction. If it worked, the yard would be replicated across the West Coast. If it failed, the Atlantic convoys would continue to shrink, and Britain's capacity to sustain the war would erode beyond recovery. The clock was now running. The first keel would need to be laid within months, and every day of delay meant another convoy sailing with fewer escorts, fewer supplies, and fewer chances of survival. Richmond Yard No. 1, September 15, 1941. The drafting floor at Kaiser's new shipyard looked more like an aircraft factory than a traditional shipbuilding operation. Engineers had divided the Liberty ship design into approximately 250 transportable units, hull sections, bulkheads, deckhouses, machinery spaces, each drawn to precise dimensions with tolerances measured in 1/16 of an inch. The goal was to eliminate the keel-up sequencing that defined conventional construction. In traditional yards, the keel was laid first, and all subsequent work radiated upward and outward from that central spine. Frames were attached to the keel, plates were riveted to the frames, decks were built on top of the hull. Each stage waited for the previous stage to complete. Idle time was inevitable. Cranes sat unused. Welders waited for fitters. Fitters waited for frame erection. The entire process was serial, linear, and slow. Kaiser's engineers proposed a different model. Hull blocks would be fabricated in parallel at off-site shops, complete with welded seams, stiffeners, and internal fittings. When a block arrived at the berth, it would be lifted into place by heavy-duty gantry cranes and welded to adjacent blocks. Deckhouses would arrive fully assembled, with hatches, ladders, and ventilation already installed. Machinery beds would be pre-fitted with mounts and piping stubs. The berth would become an assembly point, not a construction site. The blueprints reflected this philosophy. Each module was numbered, weighed, and assigned a sequence position. Lifting points were calculated to ensure balance during crane operations. Weld procedures were standardized, joint types, electrode specifications, preheat requirements, and post-weld inspections all documented in process sheets approved by the Navy Bureau of Ships and the American Welding Society. Nothing was left to chance. Nothing was left to individual judgment. To make the system work, Kaiser needed infrastructure. Rail lines were extended into the yard to bring modules directly to berthside. Truck routes were laid out to handle deliveries from dozens of subcontractors across California. Gantry cranes with lifting capacities of 20 to 30 tons were installed at each berth. Material staging areas were mapped to minimize handling time. Every minute mattered. Every foot of movement mattered. The entire operation was choreographed like a factory floor, not a waterfront craft shop. The skeptics remained vocal. Veteran shipbuilders warned that welded hulls would crack under stress, that novice welders could never maintain the quality required for ocean-going vessels, that the logistics of coordinating hundreds of suppliers would collapse under its own complexity. But the Navy Bureau of Ships assigned liaison officers to Richmond, and their reports grew increasingly optimistic. The jig tables were holding tolerances. The welds were passing X-ray inspection. The cycle times were dropping as the crews learned the rhythm of module assembly. By late September, the yard had processed its first complete hull assembly sequence on paper. The critical path showed that berth occupancy, the traditional bottleneck, could be reduced to a fraction of conventional build times if the modules arrived on schedule. The new bottleneck would be materials: steel plate, piping, electrical components, and machinery. But materials could be ordered in bulk, produced at inland plants, and shipped by rail. The constraint had shifted from scarce berth time to scalable supply chains. Richmond Yard No. 1 was now a test bed for a theory that ships could be built the way automobiles were built, the way aircraft were built, the way industrial democracy built everything, through standardization, division of labor, and relentless optimization of process. If the theory held, the Atlantic supply line would stabilize. If it failed, the losses would continue, and the mathematics of attrition would grind toward an inevitable conclusion. The next challenge was not engineering. It was training. Richmond, California, February 20th, 1942. The training campus beside the shipyard ran classes in 3 8-hour shifts. Students arrived with no welding experience and left 21 days later with Navy certification and a berth assignment. The curriculum was narrow and deep. How to strike an arc, how to maintain a puddle, how to read a weld symbol, how to identify defects. Every trainee welded the same practice joints, passed the same coupon tests, and met the same tolerance standards, plus or minus 1/16 of an inch, verified by X-ray spot checks. The skeptics had predicted failure. Master welders, they argued, required years of apprenticeship. The art of welding demanded intuition, experience, and a sensitivity to heat and metal that could not be taught in 3 weeks. But the training data told a different story. By the end of the first quarter of 1942, Richmond's weld schools were graduating thousands of certified welders per month. Pass rates hovered near 80%. Reject rates on production welds were falling as process controls tightened and fixtures improved. The key was standardization. Trainees did not need to master every welding technique. They needed to master a small set of standard joints used repeatedly throughout the Liberty ship design. But joints for hull plates, fillet welds for stiffeners, T-joints for bulkhead attachments. Each joint type had a documented procedure: electrode size, travel speed, amperage, preheat requirements. Jigs held the work in position. Fixtures controlled alignment. Quality inspectors verified each seam before the next section was added. Navy inspectors stationed at Richmond submitted regular reports to the Bureau of Ships. The welding process, they noted, was producing stronger joints than riveted construction. The heat-affected zones were narrow and controlled. Distortion was minimal. And the welds themselves, when tested to failure in Navy laboratories, showed tensile strengths exceeding 35% above riveted joints. The theoretical concerns about brittle fracture were not materializing in practice. By mid-1942, the labor pool at Richmond and the newly opened Yard No. 2 included tens of thousands of welders. Women comprised more than 1/3 of the workforce, a proportion that would have been unthinkable in traditional heavy industry. Accident rates, initially high, dropped by 40% after ergonomic improvements to jig design and torch positioning. Output per worker stabilized at 95 to 100% of male averages, according to yard production statistics and War Manpower Commission reports. The transformation was visible in the numbers. In January 1942, Richmond Yard No. 1 completed its first Liberty ship in 244 days, faster than the national average, but still far from Kaiser's target. By June, cycle time had dropped to 105 days. By September, it reached 42 days. The learning curve was steep, and it showed no sign of flattening. Every hull taught lessons that were immediately applied to the next. Every bottleneck identified in one shift was solved by the next shift. The system was adapting, learning, and accelerating. The constraint was no longer skill. It was tempo. Could the supply chain keep pace with the berths? Could the berths keep pace with the workers? Could the workers sustain the intensity of 24-hour, 7-day-a-week operation? The answer, visible in the floodlights that now burned through every night at Richmond, was becoming clear. The industrial front was no longer a metaphor. It was a battlefield, and it was running at full speed. Richmond Yard No. 2, June 5, 1942. The siren marking shift change echoed across the waterfront 3 times per day. Badge clocks registered the flow. 8,000 workers ending their shift, 8,000 beginning theirs. The yard never slept. Floodlights turned night into artificial day. Gantry cranes moved in synchronized arcs, lifting hull sections, lowering deckhouses, positioning machinery beds. The rhythm was industrial, mechanical, and relentless. Traditional shipyards ran daylight-heavy schedules, with skeleton night crews handling only essential tasks. Richmond ran 3 full shifts of equal strength. Maintenance was scheduled during shift transitions. Material deliveries were timed to arrive just before they were needed, minimizing storage and handling. Welding stations operated continuously, with fresh electrodes and gas cylinders staged berthside. Every minute of downtime was tracked, analyzed, and eliminated. The logistics behind this tempo were staggering. 56 subcontractors across California fed components to Richmond, deck plates from Oakland, piping assemblies from San Francisco, electrical panels from Los Angeles, valves from San Diego. Each supplier had to meet delivery windows measured in hours, not days. Late deliveries halted assembly. Early deliveries clogged staging areas. The entire supply chain operated on a just-in-time model that would have been unthinkable in peacetime. Inside the yard, the process was visible in the berth occupancy charts posted in the planning office. Each Liberty ship moved through a sequence of lifts. Keel sections, hull blocks, bulkheads, decks, superstructure, machinery. The cycle time per ship, from first keel placement to launch, was now approaching 17 days in mid-1942. This was not a record-setting sprint. This was the standard, repeatable pace. Hull after hull, week after week, the tempo held. The human cost of this pace was measurable. Fatigue-related incidents rose during the first months of 24-hour operations, then declined as shift rotation patterns were adjusted and rest facilities improved. Medical staff stationed at the yard treated minor injuries on-site to minimize lost time. Cafeterias served hot meals around the clock. Childcare facilities opened near the yard gates to support working mothers. The infrastructure of sustained industrial mobilization extended far beyond the berths themselves. Material flow became the critical path. Steel plate arrived by rail from mills in Pennsylvania and Ohio, traveling 3,000 miles to reach the West Coast. Pipe came from Texas. Machinery from the Midwest. Every ton had to be tracked, routed, and delivered on schedule. The War Production Board allocated rail cars to shipyard supply with the same priority given to military equipment. Entire freight divisions were dedicated to moving Liberty ship components across the continent. By late summer 1942, Richmond Yard No. 2 was completing 1 Liberty ship every 5 days. Yard No. 1 was matching this pace. Together, the 2 Richmond facilities were producing more cargo tonnage per month than the entire United States Merchant Marine had added in an average year during the 1930s. The scale was unprecedented. The implications were profound. For the first time since 1939, Allied merchant tonnage was no longer shrinking, it was growing. And the numbers were about to improve further. The debate over riveted versus welded construction was ending. The Navy had conducted its tests. The results were conclusive. Welded Liberty ships were not only faster to build, they were stronger, lighter, and more reliable. The gamble Kaiser had proposed in March 1941 was now validated by engineering data, production statistics, and the growing fleet of Liberty hulls crossing the Atlantic. The industrial method had won the argument. Now it had to win the war. Washington Navy Yard, August 18, 1942. The materials testing laboratory at the Bureau of Ships had spent months subjecting sample sections to stress, pressure, and temperature extremes. Welded plates were loaded until failure. Riveted plates underwent identical tests. The results were documented in engineering reports, stamped, filed, and forwarded to Admiral Land and the Maritime Commission. The tests showed that welded joints, when properly executed, exhibited tensile strengths approximately 35% higher than riveted joints under equivalent loading. The welded seams distributed stress more evenly across the joint, whereas riveted seams concentrated stress at each rivet hole, potential failure points under extreme conditions. Welded hulls had fewer seam interfaces, reducing the number of potential leak paths from approximately 5,000 in a riveted Liberty to under 2,000 in a welded design. Weight savings were significant. Eliminating rivet heads and overlapping plates saved approximately 60 tons per hull. This translated directly into cargo capacity, 60 additional tons of supplies, fuel, or munitions per crossing. Across a fleet of hundreds of ships, the aggregate capacity increase was equivalent to building dozens of additional hulls at no extra cost. Cost analysis reinforced the engineering findings. Welded construction reduced labor hours per ship by nearly 40%, from 1.2 million man-hours to approximately 700,000. Material waste dropped. Rework rates declined as standardized weld procedures replaced variable rivet quality. The all-in cost per Liberty ship fell from approximately $2 million for riveted construction to approximately $1.8 million for welded, a savings of $120,000 per hull, or $336 million across the planned fleet of 2,800 ships. The Navy's conclusion was unequivocal. A Bureau of Ships memorandum dated August 1942 recommended immediate conversion of all Liberty ship production to fully welded construction. The Maritime Commission concurred. By September, new orders specified welded hulls exclusively. Existing riveting lines were phased out. Welders, not riveters, would define the pace of production for the remainder of the war. The policy shift had immediate effects. Training programs expanded. Weld schools opened at every major shipyard. Electrode manufacturers ramped production. Fixture suppliers received priority allocations of steel and tooling. The entire industrial base pivoted toward a construction method that, 18 months earlier, had been considered experimental at best and dangerous at worst. Critics who had warned of catastrophic brittle fractures were confronted with data showing no such failures in service. Liberty ships were crossing the Atlantic in convoys, riding out winter gales, surviving torpedo near misses, and delivering their cargoes intact. Hull inspections after voyages showed weld integrity holding under conditions that would have loosened rivets and opened seams. The theoretical risks had not materialized. The practical advantages were undeniable. By the end of 1942, the welded Liberty ship was no longer an experiment. It was the standard, and the standard was being replicated at shipyards from California to Maine, from Texas to Oregon. The production curve was bending upward at a rate that would have seemed impossible 2 years earlier. The question was no longer whether welded ships could be built at scale. The question was whether they could be built fast enough to outpace the U-boats, and whether the U-boats, facing an enemy that could replace losses faster than they could inflict them, would continue the fight. The answer would come in the North Atlantic, where tonnage balance was about to shift in ways that German naval planners had not anticipated. Richmond and Portland, October 10, 1942. The personal protective equipment issue line ran continuously. Hard hats, welding shields, leather gloves, steel-toed boots. Women made up more than one-third of the workforce at Richmond and a similar proportion at the newly opened yards in Portland, Oregon. They welded hull plates, operated cranes, fitted pipe assemblies, and inspected completed sections. Production data showed their output matching male workers within narrow tolerances, 95 to 100% across most job categories. The transformation had occurred faster than workforce planners anticipated. Pre-war projections assumed female participation would remain limited to clerical and light assembly roles. War Manpower Commission reports from late 1942 documented a different reality. Women were performing heavy industrial work at scale, under conditions that included night shifts, outdoor exposure, and physical demands previously considered incompatible with female employment. The yards adapted. Ergonomic improvements reduced injury rates for all workers, but the benefits were especially pronounced for female welders. Adjustable jig tables allowed proper working height. Lighter welding leads reduced shoulder strain. Team-based lifting replaced individual material handling. Accident rates fell by approximately 40% after these modifications, according to safety bulletins and yard incident logs. Quality metrics showed no correlation between worker gender and defect rates. Navy inspectors evaluated welds blind. They examined X-rays and test coupons without knowing who had produced them. Pass rates were consistent across the workforce. When defects occurred, they traced back to process failures, not individual capability. Incorrect electrode selection, improper preheat, contaminated surfaces. Solving these problems required better procedures and supervision, not different workers. Childcare infrastructure expanded to support the workforce. On-site facilities opened at major yards, staffed around the clock to match shift schedules. Transportation networks grew to connect residential areas with industrial sites. Housing developments were built near shipyards, reducing commute times and enabling workers to sustain the intense pace of wartime production without collapsing from exhaustion. The social transformation was profound. Women who had never worked outside the home were now welding hull plates under floodlights at 2 in the morning. They were earning wages that exceeded what their husbands had made in peacetime. They were developing skills that had been jealously guarded by male-dominated trade unions. And they were doing it in numbers that made them impossible to ignore or dismiss. Photographs from the period show women in heavy leather aprons, welding shields flipped up, standing beside completed hull sections that weighed tons. The images were used in recruiting campaigns, war bond drives, and propaganda materials. But they also documented a reality. Industrial work was no longer divided along gender lines in ways that had seemed immutable only years earlier. The war demanded production, and production demanded workers, and workers were whoever could be trained and equipped to do the job. By the end of 1942, the combined workforce at Richmond's 2 yards exceeded 45,000 people. Women represented more than 15,000 of that total. They were not auxiliaries or temporary fill-ins. They were core production workers, performing tasks identical to their male colleagues and meeting identical standards. The yards could not have sustained their output without them. The Liberty Ship program could not have achieved its production goals without them. And the Atlantic supply line, which depended on an uninterrupted flow of new hulls, would have faltered without the labor they provided. The lesson was clear. Scarcity drives innovation, and innovation redefines possibility. The United States had entered the war with a shipbuilding industry constrained by tradition, limited by craft-based methods, and unable to scale. 2 years later, it was building cargo ships faster than any nation in history, using methods that violated every orthodoxy and a workforce that defied every assumption. The industrial mobilization was not just about factories and steel. It was about recognizing that capability existed in unexpected places, and that the only real limit was the willingness to adapt. North Atlantic, March 1943. Convoy assembly occurred at dusk. Merchant ships forming columns under the distant watch of escort vessels. Sailing orders were stamped, distributed to masters, and locked in safes pending departure. The routine was familiar, but the numbers were changing. The balance of tonnage sunk versus delivered was beginning to shift. March 1943 marked a turning point. German U-boat command, Befehlshaber der U-Boot, projected continued success based on trends from the previous year. Donit's staff calculated that sinking rates would remain above Allied replacement capacity, slowly strangling Britain's import lifeline. But the actual figures told a different story. Approximately 87 Allied merchant ships totaling 450,000 tons were lost to U-boat attack in March. During the same month, United States and Allied shipyards delivered approximately 140 ships totaling 1.1 million tons of new cargo capacity. For the first time since 1939, construction was outpacing destruction. The gap was narrow, but it was real. Every month that this continued meant more ships in convoy, more cargo delivered, more fuel and munitions available for operations. The arithmetic that had favored Germany since the outbreak of war was reversing. German naval staff recognized the shift. Kriegstagebuch, War Diary, entries from U-boat command in spring 1943 noted the growing difficulty of achieving decisive results. Allied convoys were larger. Escort groups were stronger. Air cover was extending farther into the mid-Atlantic gap. And even when U-boats succeeded in sinking merchants, the losses were being replaced faster than the convoy system could be degraded. Admiral Karl Donitz, commander of the U-boat force, summarized the challenge in reports to Oberkommando der Wehrmacht. The strategic calculation, he observed, had always depended on sinking ships faster than the enemy could build them. If that assumption failed, the U-boat campaign would transition from a war-winning strategy to a war of attrition that Germany could not sustain. The enemy's industrial capacity, he warned, was proving larger than German intelligence had estimated. The Liberty ships were central to this reversal. They were not fast. Their service speed of 11 knots made them easy targets for submarines that could manage 17 knots surfaced. They were not glamorous. Their utilitarian design prioritized cargo volume over aesthetics. But they were numerous, and they were arriving at a pace that German naval planners had not anticipated. Allied convoy reports from mid-1943 documented the change. HX and SC convoys, Halifax and slow convoy routes, were sailing with 60 to 80 merchant ships per group, up from 30 to 40 in earlier years. The proportion of Liberty-class vessels was climbing toward 50% of all cargo tonnage. When a Liberty was sunk, another launched within days. When a U-boat scored multiple kills in a single attack, the next convoy sailed at full strength anyway. The escort situation also improved. Escort carriers, equipped with anti-submarine aircraft, began accompanying convoys across the full width of the Atlantic. High-frequency direction finding, HF/DF, called Huff-Duff by operators, allowed escorts to detect U-boat radio transmissions and vector aircraft or surface ships toward the source. Radar sets, improving in range and reliability, reduced the effectiveness of night surface attacks. And the sheer number of escorts available per convoy increased as destroyer and corvette production ramped up. But the decisive factor remained tonnage. Technology and tactics mattered, but only if there were enough ships to form convoys in the first place. Without hulls, escorts had nothing to protect. Without capacity, cargo stayed in port. Without steady deliveries, Britain's ability to sustain military operations would erode regardless of how many U-boats were sunk. By summer 1943, the strategic balance in the Atlantic had fundamentally shifted. Germany was still sinking ships. U-boats were still dangerous. Convoys still took losses. But for every merchant sunk, more than one replacement was entering service. The rate of replacement exceeded the rate of loss, and that margin, narrow at first then widening, made all the difference. The question was no longer whether the Allies could sustain the Atlantic lifeline. The question was whether the pace of production could be pushed even higher, whether the methods pioneered at Richmond could be compressed further, whether a ship that took months to build could be completed in weeks or days. The answer would come from the same shipyard that had broken every rule to get this far. Richmond Yard No. 2, November 7, 1942. Foremen gathered around a large Gantt chart mounted on the planning office wall. Colored tags marked every major lift for the next hull to occupy berth 5. This would not be a standard build. This would be an attempt to compress the entire Liberty ship construction sequence into an interval measured in days, not weeks. The target was 4 days from keel to launch. The press had been invited. The stakes were high. Engineering Memorandum Number 44, dated November 5th, laid out the plan in precise detail. 250 prefabricated subassemblies would be staged berthside before keel placement. Triple crane teams would operate in coordinated lifts, moving hull sections, bulkheads, and deckhouses in rapid sequence. Welding rod stock sufficient for 96 continuous hours of operation would be prepositioned. Quality inspections would occur inline, not at completion. Navy inspectors would clear each section immediately after welding, eliminating post-assembly rework delays. The plan represented the culmination of 18 months of learning. Every bottleneck identified in previous builds had been analyzed and addressed. Material flow had been optimized. Crane choreography had been rehearsed. Workers had been briefed on their roles in a sequence where every minute mattered. The yard was betting that what had seemed impossible in early 1941 was now routine, and that routine could be compressed into a demonstration that would prove just how far industrial method could be pushed. Bureau of Ships observers arrived to monitor the attempt. They brought stopwatches, cameras, and clipboards. Their role was not to assist but to document. If Richmond succeeded, the techniques would be shared across the national shipbuilding program. If Richmond failed, the failure would be studied to prevent similar attempts from wasting resources. Either way, the data would be collected, analyzed, and filed. The ship selected for this demonstration was to be named Robert E. Peary, honoring the Arctic explorer. The irony was noted. Peary had spent years preparing for expeditions that took months to complete. His namesake ship would be built in less than a week. The symbolism was deliberate, a contrast between the patient, individual heroism of exploration and the rapid, collective power of industrial mobilization. Berth 5 was cleared. Equipment was tested. Shift rosters were finalized. Medical staff were placed on standby. The yard prepared for an operation that would run without pause from keel placement to launch. There would be no extended breaks, no waiting for the next shift to arrive, no gaps in the schedule. The process would flow like an assembly line, with each team handing off to the next in seamless succession. Skeptics predicted failure. Veteran shipbuilders noted that rushing construction invited mistakes, that welds needed time to cool and be inspected properly, that structural integrity could not be verified under deadline pressure. But the yard's engineering staff had calculated the risks and concluded they were manageable. The weld procedures were proven. The quality inspections were inline and immediate. The modules had been pre-fitted and tested before arriving at the berth. The only question was execution. On the morning of November 8, 1942, the first keel section of Robert E. Peary was lowered into position. Cranes moved in synchronized arcs. Welders struck arcs. Inspectors began their rounds. The clock was running. The press took photographs. The Bureau of Ships observers started their logs. Richmond Yard No. 2 had committed to a timeline that seemed impossible, and the only way to prove it was possible was to do it. For days, 96 hours, from keel to launch, the industrial front was about to set a record that would define what American production could achieve when necessity met method, when experience met audacity, when the question "how fast?" received an answer that rewrote expectations. The outcome would be measured in hours, witnessed by officials, and remembered as proof that victory in modern war was not only about courage under fire, it was about steel under cranes, welds under inspection, and workers under floodlights who understood that speed itself could be a weapon. Richmond, November 8 to 12, 1942. The construction of Robert E. Peary unfolded in continuous, documented stages. Time-lapse photographs captured the sequence. Bare berth at 0 hour, keel sections in place by hour 4, hull blocks rising by hour 12, superstructure taking shape by hour 24. The yard operated without pause. Shifts overlapped to eliminate handoff delays. Cranes never sat idle. Welding arcs traced seam patterns across every visible surface. Bureau of Ships inspectors maintained hourly logs. Each major section was cleared in real time. X-ray verification of critical welds occurred as soon as the metal cooled to safe handling temperature. Hydrostatic tests of compartments were conducted inline, with pressure gauges monitored by Navy personnel who had the authority to halt work if standards were not met. No such halt occurred. Every test passed. Every inspection cleared. The quality metrics held even as the tempo accelerated. 22 gantry cranes participated in the operation. Approximately 250 welders rotated through the berth in shifts that blurred together. Fixture tables controlled alignment to tolerances of 1/16 inch. Datum lines ensured that modules mated properly despite being fabricated at different off-site locations. The precision required to make this work had been built into the system over months of refinement. This was not improvisation, it was choreography. Critics who had predicted rework were confronted with inspection reports showing clean acceptance on first pass. The modular approach, which skeptics had warned would produce misalignment and gaps, instead demonstrated that standardized jigs and controlled fabrication could achieve tighter tolerances than traditional keel-up construction. The welds joining prefabricated sections were stronger and cleaner than welds laid under the time pressure of sequential assembly. By hour 48, the hull was complete. By hour 72, the superstructure was in place and machinery was being installed. By hour 90, final systems checks were underway. At hour 94, the ship was ready for launch. The official time recorded by the Maritime Commission was 4 days, 15 hours, and 26 minutes from keel placement to launch ceremony. Robert E. Peary was afloat, structurally complete, and ready for outfitting. The achievement was more than a publicity stunt. It demonstrated that the bottleneck in Liberty ship production was not technical, it was organizational. With proper planning, pre-staging, and coordination, build times could be compressed far below what traditional shipbuilding considered possible. The same techniques that built Robert E. Peary in under 5 days were immediately applied, in less extreme form, to standard production runs. Within 6 months, the national average build time for Liberty ships dropped from approximately 105 days to 42 days. Richmond's methods spread to other yards. Modular construction became doctrine. Prefabrication shops proliferated. The lessons of the 4-day ship were absorbed into the routine production tempo that would define American shipbuilding for the remainder of the war. Post-war assessments by the Maritime Commission confirmed that Robert E. Peary was not an anomaly. The ship served throughout the war without structural issues. Hull inspections after years of service showed weld integrity consistent with ships built at standard pace. The speed of construction had not compromised durability. The demonstration had proven that industrial method, when pushed to its logical extreme, could achieve results that seemed impossible under traditional assumptions. The story of Robert E. Peary became a symbol of American industrial power. Newsreels showed the construction sequence. War bond campaigns used the ship as evidence that the home front was winning its own battles. But the deeper significance was operational. Every day shaved off the build time for a Liberty ship meant more tonnage available sooner, more cargo crossing the Atlantic, more supplies reaching Britain and the Soviet Union, more capacity to sustain offensive operations. By the end of 1943, Liberty ships were being completed at an average rate of 3 per day across all United States shipyards. Richmond alone was averaging 1 ship every 5 days from its 2 yards. The numbers were staggering. The implications were strategic. Germany had planned its war on the assumption that Allied shipping would be a scarce, diminishing resource. Instead, it was abundant and growing. The U-boat campaign, which had nearly succeeded in 1942, was now facing an enemy that could absorb losses and still expand capacity. The industrial front had delivered a weapon that the tactical front could not counter, replaceable tonnage at a rate that exceeded any conceivable attrition. The mathematics of the Atlantic battle had shifted decisively, and there was no going back. North Atlantic, July 27, 1944. The bridge log of convoy HX-300 recorded a formation of 166 merchant ships, the largest convoy of the war. The majority were Liberty-class vessels, identifiable by their utilitarian profile and distinctive straight-stem bow. Escorts formed a protective screen. Destroyers, destroyer escorts, frigates, and a small escort carrier providing air cover. The convoy's gross tonnage exceeded 1 million tons of cargo capacity, a figure that would have been unimaginable 3 years earlier. German naval staff had assumed that convoy size would remain constrained by escort availability and port capacity. The assumption had been reasonable in 1941 and 1942, when every available hull was needed and losses were mounting. But by mid-1944, the constraint had vanished. Merchant tonnage was no longer scarce. Liberty ships were launching faster than they could be assigned to routes. The bottleneck had shifted from hull availability to port handling. Cranes, berths, stevedores, and rail connections now limited throughput, not the ships themselves. The composition of HX-300 reflected this abundance. Liberty ships carried munitions, fuel oil, vehicles, aircraft, and general cargo. Their standardized holds simplified loading. Their triple expansion steam engines required no specialized fuel. They burned bunker oil, which was available at every Allied port. Their crews, trained on identical machinery across hundreds of identical ships, could transfer between vessels with minimal retraining. The standardization that had made rapid construction possible now enabled operational flexibility at scale. Loss rates in mid-1944 had fallen below 2% per crossing. Improved escort tactics, better radar, and air cover contributed to this decline. But the underlying factor was numerical. Even when U-boats succeeded in sinking merchants, the losses were insignificant relative to the total capacity in service. A convoy losing 3 ships out of 166 suffered tactically but not strategically. Replacement hulls were already en route from United States shipyards. Allied convoy reports from the second half of 1944 documented routine operations on a scale that would have seemed extraordinary 2 years earlier. Convoys sailed weekly, sometimes twice weekly. Turnaround times shortened as port infrastructure expanded. The Atlantic crossing, once a gauntlet of attrition, had become a logistics pipeline operating with industrial regularity. Ships moved like freight cars on a transcontinental rail line, scheduled, predictable, and relentless. The strategic implications were profound. Operation Overlord, the Normandy invasion, required continuous shipment of supplies across the Atlantic and through the English Channel. The build-up for the invasion consumed millions of tons of cargo capacity. Without Liberty ships, the operation could not have been sustained. Without modular construction and welded hulls, Liberty ships could not have been built in sufficient numbers. Without the breakthroughs pioneered at Richmond, the timeline for industrial mobilization would have stretched beyond the operational window. Liberty ship specifications became a standard reference. 10,000 tons displacement, 441 feet length, 57 feet beam, 11 knots service speed, 7,700 tons cargo capacity. These numbers were not impressive individually, but multiplied across 2,700 ships, they represented a cargo capacity exceeding 20 million tons, a fleet larger than the entire world merchant marine of 1939. German planners had not anticipated this scale. Pre-war intelligence estimates of United States industrial capacity had been based on peacetime output and traditional construction methods. The estimates were wrong by an order of magnitude. The enemy had not simply built more ships, it had built them differently, using methods that overturned a century of shipbuilding orthodoxy and achieved throughput rates that seemed physically impossible under conventional assumptions. By late 1944, the outcome of the Atlantic battle was no longer in doubt. U-boats continued to operate, and they continued to sink ships. But the strategic calculus had shifted irreversibly. Sinking a Liberty ship removed one vessel from service for the time required to cross the Atlantic, approximately 2 weeks. Building a replacement took approximately 6 weeks from keel to delivery. The exchange rate favored the Allies by a factor of 3, and the advantage was compounding. Every month that passed saw more Liberty ships in service, more convoys sailing, more cargo delivered, and fewer U-boats able to disrupt the flow. The war's outcome had always depended on logistics. Which side could sustain operations? Which side could replace losses? Which side could translate industrial capacity into military effect? The Liberty ship program answered those questions decisively. The Atlantic was not won by a single battle or a technological breakthrough. It was won by berths, cranes, welds, and workers who understood that victory in modern war required producing faster than the enemy could destroy. The industrial front had become the decisive front, and the factories had delivered a weapon that no navy could sink. Washington, D.C., May 1945. The War Production Board assembled final tables for victory in Europe briefings. The numbers documented a mobilization that had transformed the United States from a peacetime economy into the arsenal of democracy. Among the most striking figures were those related to shipbuilding. Approximately 2,710 Liberty ships completed, approximately 130 million tons of cargo delivered across the Atlantic, and a national peak production cadence of one ship every 8.2 hours across all United States yards. Axis planning had never anticipated industrial output at this scale. German and Japanese estimates of American production capacity, based on pre-war data and traditional methods, had been exceeded by factors of 3 to 5 across most categories. Shipbuilding was the most dramatic example. In 1939, the United States built fewer than 100 merchant ships of all types. By 1943, Liberty ships alone were being completed at a rate exceeding 3 per day. The cumulative labor savings from welded, modular construction versus traditional riveted methods were estimated by the Maritime Commission at approximately 2 billion man-hours. This represented capacity equivalent to 1 million workers laboring for 2,000 hours each, an entire industrial workforce freed for other war production simply by changing construction method. The economic leverage was staggering. War Production Board analysts traced the cascade effects. Faster ship production meant more cargo capacity, which meant more supplies delivered, which meant more munitions at the front, which meant higher operational tempo for ground and air forces. The Liberty ship program did not exist in isolation. It was part of an integrated industrial system where every bottleneck solved created capacity for solving the next bottleneck. Post-action analyses by the Maritime Commission documented the learning curve. Early Liberty ships required approximately 1.2 million man-hours from keel to delivery. By late 1943, this had dropped to approximately 500,000 man-hours. By 1945, the most efficient yards were completing ships in under 400,000 man-hours. The improvement was continuous, systematic, and transferable across yards. Welding standards, modularization, rail-fed supply chains, and shift discipline became doctrine. The methods that had seemed radical in 1941 were now routine across American industry. The lessons extended beyond shipbuilding. Aircraft production adopted similar techniques. Tank production used modular assembly. Artillery manufacturing standardized components. The industrial mobilization was not a collection of separate programs. It was a coherent system applying common principles across every category of war production. The replacement versus destruction equation told the story starkly. Axis forces sank approximately 200 Liberty ships during the war, roughly 7% of total production. 93% survived to see peace. The loss rate was lower than pre-war insurance actuaries would have projected for merchant ships operating in a war zone. The combination of escort protection, convoy discipline, and sheer numbers had made individual ships survivable even in the face of determined submarine attack. Strategic campaigns depended on this capacity. The North Africa landings, the Sicily invasion, the Italy campaign, the Normandy invasion, and the subsequent drive into Germany all required continuous logistics over oceanic distances. Without Liberty ships, these operations would have been delayed or impossible. The tempo of Allied offensives in Europe was set not by tactical constraints but by logistical capacity, and logistical capacity was determined by the number of hulls available to move supplies. The Pacific Theater told a similar story. Liberty ships carried fuel, munitions, and vehicles across vast oceanic distances to sustain island-hopping campaigns. The ships were not glamorous. They did not win battles directly, but every battle depended on them. Every offensive required them. Every strategic decision was constrained by what the logistics pipeline could deliver, and the pipeline's capacity was determined by industrial method applied at scale. War Production Board charts showed the cumulative tonnage delivered by month. The curve climbed steadily from 1942 through 1945, with only minor dips during periods of heavy losses. By the end of the war, the total cargo moved by Liberty ships exceeded the entire pre-war global merchant fleet's annual carrying capacity by a factor of 2. The scale was beyond anything anticipated in peacetime planning or wartime projections. The program's cost was quantifiable. Approximately $5 billion had been invested in emergency shipyards, training programs, and production infrastructure. The return was a cargo fleet that delivered war-winning logistics and survived to serve in peacetime commerce. By any measure, cost per ton delivered, speed of mobilization, operational reliability, the Liberty Ship program represented the most successful emergency industrial program of the war. The final assessment was clear. Industrial capacity had proven to be a weapon as decisive as any deployed on the battlefield. The nation that could replace losses faster than they were inflicted, that could supply its forces more reliably than the enemy, that could translate factory output into military effect, held an advantage that tactics and courage alone could not overcome. The Liberty Ship was the symbol of that advantage, a plain, utilitarian vessel that embodied the power of method over tradition, standardization over craft, and industrial democracy over totalitarian economies. The last word belonged to the auditors and analysts, but the verdict was already written in the tonnage tallies and delivery logs. Process had proven to be a weapon class of its own. Global ports, 1946 to 1950. Surplus Liberty ships sat at anchor in harbors from San Francisco to Liverpool, their wartime service complete. Maritime Commission registry books documented sales to commercial operators around the world. Greek shipping firms purchased dozens. Norwegian companies acquired fleets. American operators converted Liberties into coastal freighters and grain carriers. The ships that had been built as temporary expedients were proving durable enough for decades of commercial use. The expectation had been that welded, emergency-built vessels would be scrapped immediately after the war. Naval architects and traditional shipbuilders predicted that the hulls would fatigue quickly, that the welds would crack under sustained peacetime operation, that the corners cut for speed of construction would manifest as structural failures within years. The predictions were wrong. Liberty ships continued operating through the 1950s and into the 1960s. Many served for more than 20 years. A few remain preserved as museum ships in the 21st century. Combat losses totaled approximately 200 ships, 7% of production. Of these, the majority were sunk by submarine torpedo or aerial attack. A small number succumbed to marine casualties, collisions, groundings, storms. The rate of losses attributable to structural failure of welded hulls was negligible. The brittle fracture concerns that had dominated pre-war discussions did not materialize at scale. When fractures did occur, they were studied, analyzed, and traced to specific conditions, usually extreme cold combined with impact loading, that could be mitigated through operational procedures and minor design modifications. The broader impact of the Liberty Ship program extended beyond the vessels themselves. The welding techniques validated during emergency ship production became standard across global shipbuilding. Post-war merchant ships adopted welded construction universally. Riveted hulls, which had dominated maritime construction for a century, disappeared from new production within a decade. The transition was complete, irreversible, and global. Modular construction methods influenced post-war industrial design. The principles of prefabrication, standardized components, and assembly line construction spread to sectors far beyond shipbuilding. Early containerization concepts drew on lessons from Liberty Ship cargo handling. Standardized hull sections inspired modular approaches in offshore oil platforms, commercial construction, and even aerospace applications. The techniques that had been developed under wartime pressure became peacetime doctrine. Training programs established during the war influenced post-war vocational education. The model of rapid skill development through standardized curricula, practical testing, and inline quality verification was adopted by trade schools, apprenticeship programs, and industrial training centers. The idea that complex technical skills could be taught in weeks rather than years challenged traditional craft guild assumptions and opened industrial work to broader participation. The workforce transformation persisted. Women who had welded Liberty ships during the war faced pressure to return to domestic roles in peacetime, but many continued in industrial employment. The precedent had been set. The barriers that had seemed insurmountable in 1940 were revealed as social conventions rather than physical laws. Post-war labor markets slowly absorbed the lesson, though full integration would require decades. Maritime Commission post-war assessments summarized the program's legacy in dry, bureaucratic language. One report, dated 1946, noted, The Liberty ship was a victory of process over scarcity. Organization outpaced destruction. The phrasing was understated, but the conclusion was stark. Industrial method had proven decisive. The nation that could organize production more efficiently, scale output more rapidly, and replace losses more reliably held an advantage that battlefield courage alone could not overcome. The strategic lesson reverberated through post-war military planning. Industrial capacity became a central consideration in national security assessments. The Cold War arms race focused as much on production rates as on weapon performance. The ability to mobilize, to scale, to sustain operations through industrial output was recognized as foundational to military power. The Liberty ship program had demonstrated these principles under the most demanding conditions imaginable, and the demonstration shaped strategic thinking for generations. The ships themselves, plain and utilitarian, became symbols. They represented the triumph of democracy's industrial potential over totalitarian military tradition. They embodied the idea that free peoples, organizing voluntarily and producing collectively, could outmatch authoritarian systems. The symbolism was not imposed retrospectively. It was visible in real time to the workers, planners, and commanders who watched the tonnage tallies climb and the loss rates fall. The Atlantic was not won by a single hull, but by a timetable that the enemy could not sink. This was the final, unavoidable conclusion drawn from 4 years of emergency shipbuilding. Strategy required tactics, tactics required logistics, and logistics required capacity. The Liberty ship program delivered capacity at a rate that exceeded every projection and overturned every assumption. The ships were not beautiful. They were not fast. They were not celebrated in the same way as battleships or carriers. But they were numerous, reliable, and irreplaceable. They kept the Atlantic lifeline open when it mattered most. They sustained offensives that liberated continents. And they proved that in modern war, the decisive battles were sometimes fought not on the front lines, but in the shipyards, where the sound of welding arcs and the rhythm of gantry cranes wrote history in steel. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.